Automatic test case generation based on Monte Carlo Tree Search algorithm. Abstract automatic test case generation is an important component of software debugging process. However, maximizing coverage is still a major problem in software testing. This paper proposed Monte Carlo Tree Search, MCTS, for automatic test case generation. The proposed MCTS test case generation method, M-TCG, maximizes branch coverage of derived test cases within the available test resources. M-TCG method formulates test case generation problem as a tree exploration problem and then uses MCTS to heuristically search optimal test cases. To evaluate the effectiveness and efficiency of our method, comparative experiments were conducted based on 17 projects with 66 non-trivial Java classes from SF110 corpus and other benchmarks. Experiment results indicate that the proposed method improved average branch coverage by 2.1% compared with DynaMOSA, a state-of-the-art evolutionary technique. Our method also decreased memory consumption by 4% compared with the existing adaptive aDynaMOSA approach. Keywords: software testing, automatic test case generation, Monte Carlo Tree Search, coverage. Introduction. In recent years, automatic testing has become widely used compared to manual testing. The aim of software testing is to provide the end users with good quality products. 1-2. Generating test cases that covers many parts of the program ensures that the software application is not error-prone. One critical task in software testing is to generate test data that satisfy a given adequacy criteria. However, the automatic generation of test case with an effective method that maximizes coverage still poses a major problem in software testing. Many researchers are focusing on evolutionary algorithm strategies for test case generation. These strategies include genetic algorithm, particle SWAM optimization, simulated annealing and many others. 3-4. The existing literature, dynamic many-objective sorting algorithm, DynaMOSA, 5 and its extension aDynaMOSA 6 generate efficient test cases. However, branch coverage is not fully maximized. Branch coverage is one of the adequacy criterion highly considered in search-based test case generation. 7, 8, 9, 10. Monte Carlo Tree Search, MCTS, techniques have successfully mitigated such complex problems. MCTS 1112 is an optimization method for finding optimal decision in a given domain. It is based on random exploration search space. MCTS method can solve complex optimization problems. 13 and has been very successful in games such as Computer Go and planning problems. 14. In this paper, we proposed the MCTS-based approach for test case generation, Mtcg. We formulate test case generation problem as a tree-based optimization searching problem. To evaluate the performance of our methods, experiments were conducted on programs acquired from SF110 corpus 15 and other benchmarks that have been used in search-based methods. 16-17. The proposed methods were compared to the state-of-art evolutionary method implemented in DynaMOSA and an adaptive approach implemented in aDynaMOSA, which extends DynaMOSA. This article is summarized as follows. In section 2 we present the related work. In section point 3 we discuss the basic structure of Monte Carlo Tree Search. Section point 4 describes the proposed Mtcg method. Section point 5 discusses experimental configuration, design, experimental results, and also threats and validity. Lastly, we present our conclusion in section 6. 2. Related research. It is important to consider the performance of software being tested more effectively and at a lower cost through the use of automated methods. The purpose of test data generation automation system for programs evaluation is to generate test data that covers as many branches as possible from a program's code, with the least computational effort possible. 18. Several meta-heuristics have been suggested for path, statement, and branch coverage. Genetic algorithm, GA, is a global search heuristic that work on the principle of Darwin's theory of natural evolution. Techniques such as 5, 6, 19 have been proposed in literature. Dynamic many-objective algorithm, DynaMOSA, which is a state-of-the-art evolutionary technique. An adaptive approach aDynaMOSA extends DynaMOSA. These studies employs branch coverage objective. Much as these methods are multi-objective, branch coverage is still not fully maximized. These technique might not scale well to very large numbers of objectives and limited search budgets. The findings of the study presented by Harman and McMinn 20 indicates that sophisticated search techniques, such as evolutionary testing, can often be outperformed by far simpler search techniques. However, many methods have been put forward to learn the behavior of local search algorithms by applying reinforcement learning. Local search heuristics have been shown to be more effective than genetic algorithms for specific targets. Lock-Osha, Tillman, Harman, and de Haller 21 introduced a version of dynamic symbolic execution which uses search-based software testing approach for handling floating-point computation. The effectiveness of their approach increased, although their study also showed that for the two solvers were no effective because it requires more execution time as in a large fitness budge. Poulding and Felt 22 in their paper. Applied Monte Carlo, which is nested to generate the programs used by Gödel test, and the results were efficient. Harnam and Preet 23 proposed algorithm which combines Monte Carlo simulation and reliability computing by randomly sampling inputs from Word file. Tests that were done at different percentages on inputs was increased. The system was able to efficiently calculate the category of the document inputted. Kazanave and Mehate 24 proposed a method that combines upper confidence bound, UCT, and nested Monte Carlo search for a single-player general game playing. Their method show transposition table improves UCT. Much as there was improvement in their work, there is still a problem of whether or not the entire tree is searched for huge data. This therefore calls for parallel MCTs to resolve this issue. Various methods have been proposed in literature for test case generation, although not much is done by these techniques to measure and analyze coverage that maximizes the number of covered items 25. A study by 26 discusses some of the limitations of genetic algorithm techniques in software testing. Generating test cases that satisfies a particular target criterion with higher coverage is still one of the challenges faced by structural testing. Thus MCTs and PMCTs for automatic test case generation are beneficial to software testing. 3. Monte Carlo Tree Search Algorithm. Monte Carlo search is a probabilistic, unique decision-making algorithm. It is efficient with an enormous amount of possibilities suitable for problems with high branching factor as it does not waste computations on all possible branches. 13. The paradigm of MCTs combines information tree with Monte Carlo simulation. Monte Carlo search incrementally builds up the search tree, and for each iteration, a tree policy is used to find the most promising child node to expand. The tree policy balances the exploration and exploitation. The four basic steps of MCTs operators are shown in Fig. 1. Fig. 1. The basic Monte Carlo operation. DGS1. In the selection step, the TM is traversed from the root until a leaf node is reached to be added to the tree. MCTs uses the upper confidence bound, UCB, formula applied to trees as the strategy in the selection process to traverse TM27. A well-known algorithm called UCB that can balance the trade-off between exploration and exploitation as seen in 1. Where UC by equals value of a node, 11 equals empirical mean of a node I, the average reward/value of all nodes beneath this node. C equals a constant, T equals total number of simulations, the number of times the parent node has been visited, Ni equals is number of times child node I has been visited. The second step is expansion, which decides which node will be added to the Monte Carlo simulation is run with random node selection. Heuristic knowledge can be used to give higher weight to promising node. This is done as a typical Monte Carlo simulation, either purely random or with some simple weighting heuristics if a light playout is desired, or by using some computationally expensive heuristics and evaluations for a heavy playout. Propagation is a step where the results of simulation is propagated upwards through the search TMAND. Each node selected in step 1 is updated accordingly. Termination. Once the time given as input expires or when all the nodes in the tree have been exhausted, the program stops expanding the tree and computes the final results. 4. The proposed M-TCG method. A program under test is taken as input and instrumented program is generated. The instrumented program is parsed and stored as a list. A control flow graph is generated from the stored data. The instrumented program executes the test data, corresponding branches are traced to check whether the test data meets the target requirement or not. Monte Carlo tree search operators play an important role in generation of test case. This method formulates test case generation as a search tree-based optimization searching problem. The node of the search tree is traversed using the tree policy starting from the root node. Tree policy is used to construct simulated test case generation tree. Once a leaf node is reached, a new state of the node is added to the tree. Monte simulation is performed with random policy and the results of the statistic is back propagated. Monte Carlo tester automatically and regularly generates new test case to monitor whether the target branches are covered or not and accordingly update Monte Carlo tree search parameters to lead new test to traverse uncovered branches. Test cases are chosen from their domain at random and the algorithm generates new test cases in order to achieve the target branch. Suitable test case that executes along the target branch is generated. Mtcg algorithm. This approach uses MCTs to generated test cases. The program branches are sampled and executed the algorithm. The output of the algorithm is a program branch that leads to highest coverage in the program. Algorithm 1 shows the general algorithm for MCTS where S0 is the initial state, the max is the maximum tree depth. Is node set, M is edge set, TM is a search tree, a test case generation tree where each node represents a state of test case generation. Initially, TM has only one node at the root. The instrumented program, the current rollout, simulation, initial state, and the maximum tree depth are the inputs while the out is a test data arrays for the target node. The completed simulation is initialized and statistics are initialized to 0. The search tree containing nodes and edges are also initialized. While the stopping condition is not reached, a node is selected. Selection, we select the child node from root node S0 that represents states S leading to highest value of Q, SA. The tree policy as to traverse a tree TM is determined by 2. Algorithm 1, the general algorithm for MTCG method. Input, instrumented program. Initial states 0, max tree depth max, simulation and rollout played. Output, test data arrays for the target node. 1. Initialize. The completed simulation complete point 0. A search tree TM each with node set VMS0. An edge set M. Where the statistics are initialized to 0. 2. While timeout is not expired and tree is not exhausted do. 3. If target is reached, update the test data that reaches the target node. Continue with next branch. 4. And 5. While complete and do. 6. Node selection. Select a node using UTC formula by traversing over TM starting from root node S0. Node is selected according to equation 2. A successor of the node is selected based on if its depth exceeds the max or not. 7. Expansion. Choose action at state S to expand. 8. Simulation. Perform a simulation on the current node. 9. Wait until a simulation is complete and get return. 10. Back propagation. Update the current move sequence with the simulation result. 11. If complete plus 1. Terminate the current process. 13. End. 14. End while. 15. End while. 16. Return the best action for the initial state S0. Where A is an action, S is the current state, A, S is a set of actions that are in state S, Q, SA is a value of an action in state S, N, S represents the total number of simulation, N, SA is a number of times an action is sampled in state S, C is the uncertainty constant to be applied when calculating the bonuses of each action. C0. Expansion. An action for expansion is selected at state S and test case state is loaded. Choose the node that maximizes the UCT value. We keep doing this until we reach the leaf node. A new node added to the tree if it does not already exist or if the node already exists in the tree and check number of times a link was chosen for each action link. Simulation. Perform simulation until a result is achieved. Simulation is performed using a random default policy. The statistics are computed and the numbers of visits for each action are obtained per each play turn. An integer representing the result is returned. Search tree TM with node set VMS0, each corresponding to its state S that has been seen during simulations. Each node contains a total count for the state, N, S, and an action value Q, SA, and count N, SA, for each action A. A default policy is used to roll out simulations to completion. Every state and action in the search tree TM is evaluated by its average value during simulations. After each simulation with value V, each node in the search tree TM updates its count, and SA. Q, SA, equals 1 N, SA, dot 2 N, S, I equals 1, SA, 6, 3. Where, N, SA, is the number of times action A has been selected from state Sn, S, is the number of times a node has been played out through state S6 is the result of the if simulation played out from S, and 2, SA, is 1 if action A was selected from state S on the if play out from state S or 0 otherwise. Back propagation, update the current move sequence with the simulation result. The tree to which the node belongs is used to search for a node, also used to update tree statistics, including number of nodes and average depth. Update the data for the tree by iterating through all nodes. The weight of a node is its estimated value. A given reward is added to the total rewards for an action. An integer representing the action is selected and its reward added to approximate the test case theoretic value of moves. Termination: once the time given as input expires or when all the nodes in the tree have been exhausted, the program stops expanding the tree and computes the final results. B-test data model. The basis of the model is simple: the path selector identifies the paths. Once a set of test paths is determined, the test generator derives input data for every path that results in the execution of the selected path. The test generator provides the selector with feedback concerning paths which are infeasible. For example, a program P with directed graph G equals V, ESE, consisting of a set of vertices, nodes, and edges E equals NMNM.V, connecting the vertices. Each node denotes a basic block which itself is a sequence of instructions. It is important to note that in every basic block the control enters through the entry node and leaves at the end without stopping or branching except at the end. Basically, a block is always executed as a whole. The entry and exit nodes are two special nodes denoted by S and E respectively. An edge in a control flow graph represents possible transfer of control. All edges have associated with them a condition or a branch predicate. The branch predicate might be the empty predicate which is always true. In order to traverse the edge, the condition of the edge must hold. If a node has more than one outgoing edge, the node is a condition and the edges are called branches. The test data constructs the program flow graph, select the path and generate test data. The paths are identified by the path selector. After determining a set of test paths, the test generator derives input data for every path that results in the execution of the selected path. Essentially, our aim is to find an input data set that will traverse the path chosen by the path selector. The solution will ideally be a system of equations which will describe the nature of input data so as to traverse the path. In some cases the generator provides the selector with feedback concerning paths which are infeasible, etc. Fig 2 shows the process of test data generation. Fig 2 test generation. The flow graphs consist of nodes representing decisions and edges showing flow of control. The flow graph is constructed by replacing program control statements by equivalent diagrams. Each branch in a conditional statement is shown as a separate path. An arrow looping back to the condition node denotes a loop. Test cases are determined from the implementation of the software. A test case is a complete path from the entry vertex to the exit vertex of a flow graph. The function takes as inputs the generated values of variables as test cases, involved in the path constraint. It consists of decision-making statements. V. Experimental configuration and design. A case study. The projects were obtained from SF110 corpus and other search-based software testing benchmarks. 10 Java projects whose average branch coverage is greater than 70% were randomly selected as seen in table 1 to study the effectiveness of our method and DynaMOSA technique in terms of branch coverage. The selected projects have a total of 56 non-trivial classes. The second set experiment was conducted on Java projects randomly selected from subject projects used in the existing research paper 6. The projects were obtained from different benchmarks such as SF110 Corpus 15 and other benchmarks used in the existing research paper. 7 Java project with non-trivial classes, with cyclomatic complexity below 5, were randomly selected as shown in table 2 to study performance of our methods compared with existing DynaMOSA and aDynaMOSA. Each run was repeated 50 times. B. Experimental design. The proposed Mtcg method is a test data generation method for automatic generation of test cases guided by Mcts algorithm to derive test cases. This method automatically generates test cases for Java classes, targeting branch coverage criterion. Program's branches are executed at least once. Both the true and false branches of all conditions must be executed. For example, in a decision like if statements, the conditions should be at least once true and once false during testing, and thus all branches should be taken. A batch of test cases are generated, executed, and the branch coverage is determined. We proposed MCTS method for test case generation with the aim of maximizing branch coverage. Each of these research questions were investigated in the light of branch coverage criteria alongside other metrics, such as the runtime and heap memory consumption. The study is designed around the following research questions. RQ1, is M-TCG effective for generating test cases in terms of branch coverage criterion? RQ2, how does the M-TCG method perform compared to DynaMOSA on branch coverage? RQ3, what is the performance of M-TCG in reducing runtime compared to existing DynaMOSA and aDynaMOSA? RQ4, what is the memory consumption of Mtcg compared to DynaMOSA and aDynaMOSA? In order to answer the research questions, two sets of experiments are performed to compare the effectiveness and efficiency of the proposed Mtcg to the existing methods. For each subject program, we measured average branch coverage achieved on the programs, alongside other metrics, such as the number of test case generated and the elapsed time. Branch coverage criterion is used measures the extent to which a set of test cases covers a program is used for calculating branch coverage as shown in 4. Branch coverage equals covered branches total branches to be covered asterisk 100%, 4. See experimental results. The statistical difference is measured with Wilcoxon test and we used Cohen's d to quantify improvement. Our cutoff for significance is 5%, p-value equals 0.05. A result below 5% means significant does exist. A result above 5% means that we can't conclude that a significant difference exists. Effect size quantifies the magnitude of difference found between the variables of our technique and the existing techniques used for comparison. Cohen's d equals 0.2 is a small effect size, d equals 0.5 represents a medium effect size and 0.8 indicates a large effect size. Logger effect size means greater height difference between our approach and the existing approach for comparison. Effect size less than 0.2 means the difference is negligible although significant. To answer our research question RQ1, experiments were conducted and observation from the experiment results show that the proposed method effectively generate test cases and achieve branch coverage with fairly good performance. Our method's performance was compared with the performance of the existing methods. To answer research RQ2, experiments were performed on 10 randomly selected projects and each run repeated 10 times. Table 3 shows the results of mean branch coverage performed by Mtcg and DynaMOSA methods. Out of 10 projects, Mtcg performed better than DynaMOSA in 5 projects. Mtcg achieved an average coverage of all the 10 projects by 90.77% while DynaMOSA achieved an average coverage of all the 10 projects by 88.71%. We can observe that for all the projects, DynaMOSA covers 887.06 total percentage branches while Mtcg covers 907.85 total percentage branches of all the projects. The min branch coverage and max branch coverage column data are for our method and can be used to get the range between the minimum and maximum coverage of the 10 runs. Fig 3 shows branch coverage for both methods with the effect size of 0.25 and p-value of 0.28. The result for Mtcg shows relative increases in mean branch coverage with small effect size. Hence Mtcg method achieved an improvement with weak mean branch coverage. Experiment results show that Mtcg method improved mean branch coverage by 2.1% compared with DynaMOSA. To answer our research question RQ3, an experiment was conducted on 7 projects with each run repeated 50 times. Table 4 and Fig 4 show that Mtcg outperformed DynaMOSA and aDynaMOSA in only 2 projects out of 7 projects. The average runtime of Project FreeMind and JSecurity is lowest in Mtcg than in DynaMOSA and aDynaMOSA. The mean runtime of all projects in Mtcg is greater than that of DynaMOSA and aDynaMOSA. The effect size is 0.68 and the p-value of 0.18 when comparing Mtcg and DynaMOSA. Since the effect size is greater than 0.5, this therefore the mean runtime of Mtcg has a strong effect size. The proposed technique achieved the highest mean runtime when compared the existing DynaMOSA and aDynaMOSA. So to generate tests and achieve coverage, the proposed method requires more runtime. Comparing Mtcg and aDynaMOSA, the effect size of is 0.33 and a p-value of 0.31. So there is a relative increase in mean runtime with a weak effect size. This therefore means that aDynaMOSA require less runtime to achieve branch coverage and generate test case compared to our Mtcg method. To answer the research question RQ4, experiment was conducted on 7 projects and each run was repeated 50 times. Table 5 and Fig 5 show that the average memory consumption of all projects in Mtcg is about 14 times less than that of DynaMOSA and aDynaMOSA. Comparing Mtcg with DynaMOSA, the effect size is -1.67 and a of p-value of 0.04 indicating that the relative decrease in the mean of heap memory usage and the p-value shows there is a statistical significant difference between Mtcg and DynaMOSA. Considering Mtcg and aDynaMOSA, the effect size and p-value is -1.65 and 0.04 respectively. Here the effect also decreased the mean of memory consumption. Mtcg method consumed less memory than DynaMOSA and aDynaMOSA when generating tests. The average memory consumption of all the projects in our method is about 14 times less than that of DynaMOSA and aDynaMOSA. Therefore the proposed method outperformed DynaMOSA and aDynaMOSA by achieving 4% decrease in statistical memory consumption. Summary of the results. Experimental results showed that Mtcg method achieved the highest mean branch coverage when compared to that of both DynaMOSA and aDynaMOSA. The effect size tells us there is a strong increase in coverage when using Mtcg over DynaMOSA. Mtcg method outperformed DynaMOSA and aDynaMOSA by achieving the lowest memory consumption. However, Mtcg achieved a lower runtime than that of DynaMOSA and aDynaMOSA in only 2 out of 7 projects. The proposed technique achieved the highest mean runtime when compared to that of both DynaMOSA and aDynaMOSA. Threats to validity. Although Mcts is powerful heuristic search method, its computational cost is expensive, especially in rollouts to construct the search tree. In our future work, we will introduce parallel Monte Carlo tree search. After implementing parallel Monte Carlo tree search, we will compare the performance of our 2 methods using DynaMOSA and aDynaMOSA techniques on the same data set. The choice of existing techniques and tool for comparison is also a possible threat. There are limited recent publications for test case generation dealing with branch coverage and having available dataset for Java projects. For future work, further experimental studies are required to solve the identified limitations of our tool. The external threat to validity arises from the quality of Java projects selected and the scale used to select the projects. 6. Conclusion. We proposed MCTS method for automatic generation of test cases. The proposed method solves test case generation problem as a tree exploration problem and heuristically searches optimal test cases. A prototype system was designed and implemented to evaluate the effectiveness of our method on branch coverage and study the performance of runtime and heap memory consumption. Experiments were conducted on the popular test data sets from SF110 corpus and other benchmarks. 2 sets of comparative experiments were performed on our method and promising results were obtained by our method. Experimental results showed that the Mtcg approach generates test cases with improved average branch coverage of 2.1% of all the subject projects over DynaMOSA. In addition, our method significantly decreased heap memory consumption by 4% over the existing DynaMOSA and aDynaMOSA. However, for our method, more runtime was required to generate test cases, and for this reason, one of our future work will be to find solution to this matter.